This is a hybrid, if you like, a hybrid model. This is a cross between the length model and the area model, right? Essentially like a number track. And one of the positives or advantages of the length model is you can go easily beyond 1. If I use that set model of the eggs to go beyond 1, I just need more cartons of eggs. And you start seeing where is one hole. We've sort of lost the picture of where one hole is again, right? So it has that advantage. It's also very good for operating the length model. You take this example. What's the number one answer for that? What do children say the answer is? What's the number one answer?
11 over 20.
Very good, 11 over 20. Which, as you know, is wrong. But if you use a number line model or length model, it's quite easy to show why that is wrong. Where is 7/10? That's here. I want to add to it 4 more tenths. So what is that? It's really like a jump of the 7 from the 0 and another jump of 4. And what is that? It's 11/10. Clearly shows why it's not 11/20. This is one of the elaborations. If you look on page, I think it's on page 30, halfway down, you might want to highlight it. It says counting forwards and backwards by familiar fractions, halves, quarters, thirds, fifths and tenths. So again, because you can show more than one, it's nice to be able to, you can count the wholes, but you can also come back here and count the parts. So that's what they're expecting you to do. Is when you do that, it also, you can satisfy this other elaboration, converting mixed numbers to improper fractions in the reverse. So here we have proper fractions, right, such as 3/5, and over here we have the improper fractions, such as 8/5. But if I wanted to convert this, 8/5 is the same as 1 and 3/5. Okay. What other elaborations do we have here that are worthwhile looking at? Demonstrating, that's on the previous page, back to page 29 you might want to look at. Demonstrating equivalence of fractions such as, on a number line. So we can divide the number line into fractional parts. Then we might decide, let's go back and divide it into more fractional parts. What else do we do? Divide each quarter into a half again, put some more increments in there, and mark this in, which then helps us to see the equivalent fraction. 1/4 or 1/4 is the same as 2/8, or 3/4 is the same as 6/8. We tend to do that, don't we, on what you would call a fraction wall, which is again a hybrid between a length model and an area model. But this is talking about such as on a number line. So if you do it on a number line, that's what you'd expect to see. This is the point down on the very bottom of page 29. Well, not the very bottom, sorry, it's the second last one if you like. Recognising the relative size of fractions depending upon the size of the whole. You can see 3 oranges and you can see 3 apples. Now, is 3 the same in those particular 2 cases? No, well, no, they're not. There's 3 apples and there's 3 oranges. But the idea of 3 is still there, right? The same with here. 1/4 happens to be greater than 1/2 in this particular case. They have to know that the idea of 1/2 doesn't change. And that's what they're trying to get to here. If you look at the example they use, I kind of like this example here. The thirds of a netball court are smaller areas than thirds of a football field. That's like I was comparing here apples to oranges, saying 3 apples, 3 oranges. Well, here they're comparing thirds. Okay, so this third might be bigger than that third, as you know, but it's the idea of a third does not change. And directly above that elaboration is calculating everyday fractions of quantities. So this is where now they're going to start operating with fractions. And how do they do that? 1/4 of 24 is. So they're using unit fractions, but 1/4 of 24. How do you figure out 1/4 of 24? You're going to use division, aren't you? I know 1/4 of 24 is, well, you can show it like this. So here's the 24. There's 24 dots, there's 4 equal rows. How many in each row? In other words, I know 1/4 of 24 is 6. I know there's 6 in each row. because I know 6 fours are 24. So you're using these prerequisites here. This is most important. You have to have this in order to do that. I don't particularly think that's too difficult. I think that, you know, if you're focusing, if there's time allocated just to doing that, you'll be able to, you'll be able to teach that. So my concern is, and it's a concern for some of the writers or the people in charge was, and actually they went as far as saying teachers are going to have to let go of their pet activities. If they have pet activities of teaching tenths in year 4, they're just going to have to let it go and allow it to be taught in year 5, because if you're still trying to teach that in year 4, you won't have the time required to give a deep understanding of whole numbers. And I need to go back to my page 30 now. You probably do too. Back to page 30, because there's one more elaboration. No, it's page 29. The very last one, solving problems involving fractions as an operator. Here's 2 problems for you. There's 7 students, or 1/4 of the class who ride bikes each day, and 1/2 of the class who ride the bus. This is a year 4 type question. This is what they're going to have to be able to do. Now, how many? There's 2 ways you can solve this. Obviously, you can say, well, 7 students or 1/4. If 7 is 1/4 of the class, what's 4 times 7? There's 28 students in the class, right? Therefore, 1/2 of the class ride the bus, so that must be 14. Or maybe the students know that 1/2 is double 1/4, so you use double 7. Right? But the reason I'm showing you that is because the fractions are explicit in the problem. You can see 1/4 and 1/2, as opposed to this problem, which involves fractions but is implicitly shown. In a class of 24 students, you can see there's fractions. We're dealing and operating with fractions here. So they're the kinds of problems which you're going to be expecting in year 4 and will be, if not already, being tested through NAPLAN. Year 5, we get into more equivalent fractions, but also related denominators. This is not operating at all. This is simply saying what's larger, what's greater. 3/8 or 1/4. Again, the linear model, or hybrid between linear and area. Where's 3/8 on this mat? So just be prepared, you're going to see a lot more of these sorts of things. Right, so where's 3/8? 3/8 is here. Where's 1/4? Luckily they are related denominators. One denominator is a multiple of the other, or factor of the other, you might say. So I can utilise one of those to say, oh well, 1/4 is the same as 2/8, so 3/8 is larger. These are sorts of activities you'll be doing in year 5. And adding with them. So that was just comparison, now we're adding. So where's 5/8 on here? There's 5/8. So what we're going to do now is use a linear model, a number line, to do 2 things. We're going to find an equivalent fraction, and then we're going to use it to help us operate. 5/8, where's 3/4? There's 3/4 of 1. I need to start with 5/8 and add 3/4. So what is 3/4? 3/4, this is finding the equivalent fraction component. 3/4 is the same as 6/8. So now if I start with 5/8 and add 6/8, basically do this, I'm going to run along here, and the answer is 11/8. Right? So the linear model is good for doing that, isn't it? So I think we just got to get our head around these other models and be aware of these in order to achieve the elaborations that are in here. In year 6, we're going to be dealing with unrelated denominators. So here's some that are unrelated. One is not a multiple of the other, or a factor of the other. So what are we going to do with it? Find equivalent fractions first here. We're not operating, we're just comparing. So here's a fraction mat again. 3/4. 2/3, they're not related, so we have to look for another denominator. Well, here's one here. 3/4 is the same as 9/12. 2/3, oh, that's the same as 8/12. So what's larger? 9/12. Okay. Obviously, we work with multiples as a prerequisite, and there's a lot more number theory in here. I'm not even talking about this today. There's a lot more number theory. You'll get a lot more work on factors and multiples and prime numbers, etc.